right, folks, we're gonna go ahead and get started. Good morning. So today we're gonna be covering section 11.3. Okay, so yesterday was all about special types of series. Um, so we learned about the geometric one, we learned about the telescoping series, and we learned about the positive term or the P series, along with the special case, which is the harmonic series. And so today we're going to shift gears a little bit. We are going to take a look at some tests that work for a broader group of series. Okay. We're going to take a look at something called the divergence test. We're going to take a look at something called the integral test. And then we're going to finish off today with two different comparison tests, the basic comparison test and the limit comparison test. And with both of those, it's going to be important that we have our notes from yesterday so we can think about the geometric series, the telescoping series, and the P series, okay? But mostly the geometric and the P series. So with that, let's go ahead and get started. All right, so let's take a look at 11.3, okay? So 11.3 is really where your textbook introduces the positive term series. But yesterday I was like, here's a rule, just kind of go with it. And then I was like, tomorrow, which is today, we're going to learn a little bit more about why that is the way it is, okay? So what we know so far, we know the difference between a sequence and a series. Sequence is just the list of numbers, right? And the series is the one where we have to add them all together. So we're looking at different things. There is something about finite versus infinite. And for most of what we're going to be taking a look at, we're looking at infinite, and particularly we're looking at infinite series. Now, the last thing that we kind of talked about is convergence versus divergence in special case infinite series. So we talked about how we know when geometric series converge or diverge, how we find out if P series converge or diverge. And we've actually taken a look at the idea of convergence and divergence earlier when we looked at improper integrals, okay? But what's new is this whole list of all these other tests out there. And so we have a bunch of tests because we have so many different kinds of series that it's nice to be able to look at not just a special case, like it has to look like a geometric or it has to look like a P series, but that we could expand it to look at series that are more than just some of those fundamental ones. And so today we're going to be taking a look at the divergence test. Okay, so that's where we're going to start today. We're going to start with the divergence test. And then we're going to move our way into the integral test. And at the very end, we'll finish off with the basic comparison test and the limit comparison test. Okay. Those are the four that we're going to take a look at today. Tomorrow, we are going to finish what we have for exam 4 with the alternating series test. Okay, so this is 11.4. After that, after our exam on Thursday, we're going to come back on Monday, Tuesday, Wednesday. We'll have a chance to look at 2 more tests, specifically the ratio test and the root test, okay? These are not on exam 4. Okay, these are not on exam 4, but the other 5 that we highlighted are going to be on exam 4, okay? But that means that the ratio and the root test could be fair game for the final exam, all right? So we're learning 5 of these 7 tests, and for this section, and then when we come back next week, we'll finish off with the ratio test and the root test, okay? So that's where we're headed over the next week. And with that, let's get started with our divergence test, okay? So our divergence test is very similar to what we've already seen, okay? We didn't actually put a name on this before, but when we were looking at sequences, so 11.1, when we were looking at sequences, one of the things we did is we said, what happens when we plug in infinity? And we knew that if our last term was getting to infinity, that sequence was going to diverge. But if that last term were going to a number, then that sequence was converging, okay? But what we're looking at now is how do we apply the same sort of idea to a series? And so let's take a look at number 1 over here. Number 1 says you have this infinite series, and the a sub n is 4n squared minus n cubed over 10 plus 2n cubed. And so what we're going to do is we're going to apply this divergence test by doing this. We're going to take the limit as n approaches infinity of our a sub n. So this right here is our a sub n. So we're going to take the limit as n approaches infinity of 4n squared minus n cubed over 10 plus 2n cubed. Now we're going to go through L'Hopital's right now, but hopefully we can kind of catch on to some patterns as we move and maybe not have to use L'Hopital's as much, okay? So if we plug in infinity, we're going to get negative infinity on the top, and we're going to get infinity on the bottom. And when we have that, that is a case where we need to use L'Hopital's if we want to find the limit. So let's go ahead and apply L'Hopital's. We're going to take the derivative of the top, which will give us 8n minus 3n squared, and the bottom, which will be 6n squared. We pause, we plug in infinity again. We're going to get negative infinity over infinity, which means we have to use L'Hopital's again. And so when we do that, we have the limit as n approaches infinity of negative 6n over 12n, which gives us negative infinity over infinity. So we have to use L'Hopital's again. And that's going to give us the limit as n approaches infinity of negative 6 over 12. Okay, so at this point, when we plug in infinity, it doesn't actually impact our behavior here. And so what we get is that negative 1/2 is our answer, okay? But what does that negative 1/2 stand for? Okay, so this negative 1/2 is the number I get out when I put infinity into the sequence. That means that this is the last term in the sequence. Okay. So it's important as we're doing all these things to understand like what it is that we're finding and not just like plug in things, follow some rules, and kind of hope for the best, okay? So here we have negative 1/2 as the quote unquote last term in the sequence. Now what that means in terms of series is this. If the last term is a number, okay, the last term is a number that's not 0. What that means is you're always adding something more to your sequence or to your series, okay? So this means we are adding, we're always adding something to our series. And so if we're always adding something else onto our series, what that means is that it is divergent. Okay, that our infinite series does not converge because we're always adding something more. Right? Does that make sense to folks?
Yes.
Yeah.
So I do have a question about that.
Okay.
I thought that yesterday it was the opposite, no?
What was the opposite? There's so many tests, you really have to be careful about what situation you're talking about.
So I thought that yesterday, whenever we did the limit test, if we got a number, then our AN was converges.
Right, for a sequence. But we're not talking about sequences anymore. We're talking about series.
Oh, okay. All right. Thank you.
Okay. All right. I'm really glad you asked that question. I think that was, I had a lot of the similar questions when I was learning about sequences and series for the first time, because we really, I think the thing that I know I missed the boat on is I didn't really understand like what I was sort of applying and what it meant, right? So that's why I wanted to write this part out, that this number, this -1/2, if I were looking for the sequence, I would say it converges. But the series, when I add up all the terms, that does not converge. Okay, so because a sequence converges doesn't mean that the series also converges. So we have to be really careful about like what rules we're applying to what. Okay. Okay. So let's take a look at example number 2 and kind of see from there. Okay. So number 2, I know that this is an infinite series, again, because it says infinite series at the top, but also because of the sigma in the front. As soon as I see that sigma, I'm thinking, oh, I have to add up all the terms. So if I take this a sub n, right? So this, just like example 1, this is my a sub n. And I wanted to see what happens, like what does the last term in the sequence get to, right? We knew in example 1, the last term gets to -1/2. I want to figure out what the last term for n plus 1 over n is. So to find that last term, I'm going to take the limit as n approaches infinity of my a sub n. I want to find out that last term. So let's plug in infinity. We get infinity over infinity. That means we need to use L'Hopital. Okay. Pretty straightforward derivatives here. I get 1 on the top. I get 1 on the bottom. So that means that my quote unquote last term in the sequence, right? Because we're looking at in the sequence, is 1. So like before, it means I'm always adding something to our series. Okay, not my sequence, my series. I'm always adding something to the series. So therefore, this series diverges.
May I ask a clarifying question?
Sure.
So the main difference between a sequence and a series is that in a sequence, you will keep adding the numbers until you basically you reach that a of n, that 1, and then you stop adding, which is why it converges. But in a series, it technically you will never ever stop adding.
Not quite, James. So a sequence is just the list of numbers. We're not adding anything.
Okay, it's just a list of numbers until you get towards that number right there, because it will in a sequence. It will eventually, your list will eventually hit 1.
Yes, like all
Okay.
the end values are going to be super, super close to 1.
Okay, and then in a series, you're just going to be adding them basically.
Yes, yes. So you could think about it in the series. I always just keep adding 1. So if I keep adding 1, it's never going to converge to a singular value.
Yeah, I get that why the series will diverge is because you're never going to stop adding.
Yeah, yeah,
So for a sequence,
yeah.
we get a value that converges, but for the series, we're always adding something, so it's divergent.
Correct, correct.
Okay, cool.
Okay.
And is that why that whenever you have a series and it equals 0, it will converge, because eventually you're going to keep adding 0 and it won't change your value?
Correct.
And that's what I was going to ask.
Yeah. All right. So really, really good thinking here going on, okay? I have to say, as someone who absolutely had no idea what she was doing the first time she learned about series and sequences, like, I love that you're able to engage in these conversations, because I was like, I think I didn't ask these questions. I was like, I don't know, this is a rule. I guess I'll just follow it, right? But it didn't get me very far. So I love that you guys are asking these questions. Now, let's kind of maybe zoom back to pre-calc for a bit, and just take a look at just the a sub n, okay? So if I gave you y equals 4x squared minus x cubed over 10 plus 2x cubed. So basically what I had for my a sub n, right? But with x's. So we've seen this kind of function before. We've seen this, and these are called rational functions, where we have sort of a numerator and a denominator, and sometimes they have, it was our first introduction to like wholes and vertical asymptotes, and all that kind of stuff. But it was also our first real introduction to something called end behavior. Okay. So when we learned about end behavior back in the day, we learned a set of rules, okay? So it was like, oh, you compare the degrees of the top and the bottom. And depending on the relationship of the degrees, we could determine what that end behavior was. And so there was one of those rules where if the degree of the numerator, which is 3, and the degree of the denominator is 3, if those are the same, then the end behavior is going to be a horizontal asymptote at y equals the ratio of the coefficients. So the coefficient on the top is -1, and the coefficient of x cubed on the bottom is 2. Well, where have we seen this number, -1/2? That was our sort of ending terms in the sequence, okay? So this horizontal asymptote being at y equals -1/2 is really the same thing as saying, I'd like you to see what the end terms of this sequence go to. So it's not a coincidence that those two values are the same, okay? Now, some of us, we like L'Hopital's because it's most of the derivatives are pretty straightforward, right? So we could do, how many times did we do L'Hopital's? 1, 2, 3. We did it 3 different times. But it's not wrong to look at your initial sequence and notice that, that this power and this power are the same, and therefore the end behavior is going to be y equals -1/2. And so if you graph this, all the end values at the right end should be getting very close to -1/2. Okay, so that's sort of like a shortcut way that we can get to that. But we really do have to make sure we remember the correct rules for the power comparisons, okay? The reason I bring that up is because I think it's also an effective way to take a look at number 2, right? So if we look at number 2, I look at the powers. The power on the top is 1, and the power on the bottom is 1. And when the powers are the same, we know that we have a horizontal asymptote at the ratio of those coefficients. So 1 over 1 or 1. And again, it should not surprise us that our horizontal asymptote is the same as quote unquote our last few terms of the sequence, okay? So that's one thing that I think makes sequences easier to think about, because they're very similar to the graphs that we are used to seeing. And we said last week, if it flattens out, it's going to converge. And if it goes up or down, it's going to diverge, okay? We have to modify that statement a little bit for series, okay? So far we're seeing we could get a number at the end and it's still going to diverge, okay? So let's do one more example here, and then we'll talk about this divergence test. So in this case, let's do it sort of the long way, the official divergence test, which is I'm going to take the limit as n approaches infinity of my a sub n. And so I get 1 over infinity, which goes to 0. Okay. Now that means that towards the end, I'm sort of adding 0, like the last few terms are getting really close to 0, okay? But what did we learn yesterday about this kind of series? First of all, what kind of series is it, and what did we learn specifically about its convergence or divergence?
Divergent, harmonic series.
It is a harmonic series, good. And that harmonic series, remember, is just a special case where p equals 1, or the power of n equals 1. And so we know that harmonic series, they diverge based off of what we talked about yesterday. So it looks like we're getting 0 at the end, but it still diverges. Okay. So let's see what this divergence test does tell us, but also let's take a look at what it does not tell us, okay? So the divergence test says this: if the limit as n approaches infinity of a sub n is not equal to 0, then the series will diverge. Okay. So if you take the limit as n approaches infinity and you get -1/2, like in example 1, or a 1, like in example 2, you know right there that series is going to diverge. Does that make sense?
Yes.
Yeah. Okay. But here's sort of a second part to this, okay? Because it's important to know what it tells us, but it's also important to know what it does not tell us. If the limit as n approaches infinity of our sequence equals 0, like in example number 3, right? We took the limit, we found sort of what the end terms or the end behavior is. If we take that limit and we get 0, then here's the bad news. Our test is inconclusive. Okay. So good news about the divergence test. Super easy to plug in infinity. If you get a number, awesome, you're done. You get a number that's not 0, you're done. You know it diverges. Super easy, okay? But with some of sort of these easier tests comes this other part, which is, but if you get 0, it might converge, it might diverge. We don't really know. We have to explore further, okay? So we know based off of yesterday that example number 3 diverges, but based off of our solution here, we would have to say that the divergence test is inconclusive, and we would have to use another test or other knowledge to determine whether that series converges or diverges. Does that make sense?
Yes.
Got one yes. How are other people out in the cyber world doing?
Yes.
Yeah.
Yes.
Okay. so divergence test, really good if you have a sneaking suspicion that it's going to diverge. Plug in infinity, see what you get. But it doesn't really tell you anything else other than it diverges. Okay. So,
I have a question about example 1 and 2.
for sure.
So is it not correct to, like, if we are able to recognize that there are 2 of the same exponents at the top and the bottom, is it not correct to use that to figure out if it diverges or not?
It is totally fine to do that. I think when I am working through problems, I often shortcut things myself. So, yeah. So
Okay, thank you.
Yeah, if you invested in that knowledge in pre-calc and you're like, when am I ever going to use it again? Here you go. All right, it's a shortcut for a lot of stuff here. And also, again, if you take like discrete, it'll definitely be useful too. All right. So one thing that I tried to do was sort of at the end of each test talk about like when you might want to use it or what the limitations are. I would encourage you to reframe this in your own words as you need, add to it as you need, add to it as you do different problems. But I think it's important like to think about when you might want to use it, because we're going to learn so many, but also what does it tell you and what does it not tell you, okay? So when we can use the divergence test, if it seems like your series terms may not converge to 0, like you have a sneaking suspicion that maybe the degrees are the same, you know you're going to get a horizontal asymptote that's not at the x-axis, that's probably a really good time to use the divergence test, okay? And another good time, like that's just something to really keep in mind, because as we go, we're going to layer on so many other tests that are going to be more challenging or only for this case or only for that case. So it's kind of nice to know that you have one that will tell you it definitely diverges, okay? But the limitations, it only tells you whether a series diverges. It does not tell you if it converges or not. And it's not like yesterday where it tells you the value that the series converges to, okay? So like the number you get out, if you get a number that's not 0, it diverges. But if you get 0, it doesn't mean that the series converges to 0, okay? So in quiz number 13, if you haven't taken a look at it yet, I just put it up last night, so it's okay if you haven't. But there are a few questions in the beginning where I'm like, use this test, use this test, use this test. But then at the second half of the quiz, I'm like, here are some series. I'd like you to choose 2 tests to use to find out whether it converges or diverges, okay? So the point behind that is that you can use a multitude of tests as long as they fit certain constraints. And some of them might give you information, more information than others, and just kind of be comfortable with knowing that you can use more than one test for most of the series that we see, okay? All right, So let's take a look at, I don't know why I like this one so much, but I really like the integral test. But I think that's really because I like integrals. So if you are someone who is strong at integration, I think the integral test is not a bad test to use, okay? It gives you a little bit more information than the divergence test. And I think it helps kind of keep those integrations fresh for us, okay? And the good news is I really only use the integral test, and I would only encourage you to use the integral test when we're looking at things that are quote unquote easy to integrate. So like power rule or special integrals, like maybe some of the inverse trig ones, or natural log, or ease, or maybe even integration by parts, but mostly like u sub, like that kind of level, like Calc 1 integrals. So if you see something that looks like a Calc 1 integral, it might not be a bad idea to try this integral test, okay? So let's take a look at example 4, which I know is exactly like example 3, which is exactly like what we looked at yesterday. So we already know that this is a harmonic series and that it's going to diverge. But let's use the integral test to confirm for ourselves that it diverges, because the divergence test was like, I don't know, try another test. And then yesterday was like, here's a rule. I don't know why, but just believe it. So let's use this integral test to prove for ourselves that a harmonic series diverges. So here is the integral test, okay? The integral test is basically saying, I'm going to take the integral from the bottom number, which is 1 in this case, to the top number, which is infinity, of 1 over x dx. So it's very similar to our whole unit on improper integrals. And so since we can't really integrate with that bound of infinity, we're going to take the limit as t approaches infinity, integrate from 1 to t of 1 over x dx. Now I'm going to take the limit as t approaches infinity. The integral of 1 over x is none other than natural log of x. And I'm going to plug in t, and I'm going to plug in 1. Okay. So let's see what we get. We get the natural log of infinity minus the natural log of 1. Now let's go over some of these important values again. Natural log of 1 is equivalent to what?
0.
Yeah, this goes to 0. It doesn't go to 1. It doesn't go to infinity. It doesn't go to negative infinity. It goes to 0, okay? Natural log of infinity, that goes to infinity, okay? It continues to rise. It's slower than a lot of the other functions, but it's still rising. And so at the end, we get infinity. And we know that we get something that diverges, okay? So this is one way that we can use some of the stuff we already learned along with this new rule to kind of say like, hey, we can apply this for our series as well. It's not just for our integrals, but it's also applicable to our series, okay? So here's a very short explanation of sort of why this is, okay? So let's imagine for a moment that we had our 1 over n graph, okay? So 1 over n, like 1 over x, it's got like this branch here and this branch here. But we don't really want to worry about this negative part because our n values go only from 1 to infinity, okay? So that's why I'm only looking at this right-hand branch here. And now, before you learned this is an integral, this is like your reverse derivative, hopefully you spent a little bit of time sort of exploring this idea of area, because remember, at the end of the day, an integral is really reflective of the area between the curve and the x-axis. And so if we take a look at this curve, right? So here's our curve. We're sort of using these green rectangles to approximate the area. Now, looking at the diagram, is that an overestimate or an underestimate?
Over?
Yeah, this is an overestimate, right? I've got a bunch of the green rectangles that are above this red curve. So this is an overestimate. And that's going to be important as we sort of think about why this whole rule works, okay? So if you look over at this top part over here, this is just like an approximation of the area, okay? Now, this area, because remember when we're looking at series and sequences, we're looking at not the whole curve, but like singular points. We're looking at like 1 and plugging in 2 and plugging in 3 and plugging in 4, but we're not looking at plugging in the decimal values because we're counting positive whole numbers, okay? So that's why here I only have the whole numbers put into the 1 over x. Now, all of this top part gives me the green area. Okay, that gives me the green area that I have in that picture on the left. Now, if we say that this is an overestimate, then we know that the area is going to be larger than the actual integral that we see. Okay. And as we'll take a look at in the next test, if you have something that diverges here, then anything bigger than that will also diverge, okay? So this is the smaller value, and the smaller value already is like counted within our areas of our series. And we know if this one diverges, then anything bigger than it also has to diverge. Okay, so that's why when we got the infinity here, we could say that it diverges. Now, we're not going to go through a visual and the area for every single problem, but I just wanted to give us a little bit of a flavor of like why this integral test works, okay? So let's kind of try our hand with example number 5 over here, okay? Now, based on yesterday, what do we know about this series and its convergence or divergence?
It's harmonic and p equals 2.
It's not harmonic. Harmonic is only when p equals 1.
Okay.
Okay. So what is it called when in general?
Positive term series.
Yeah, so it's a p series or a positive term series. The harmonic is a very special subset of that, okay? So let's just be careful with that language. We have a p series here, and then the second part of what you said is correct, p equals 2, okay? And we know that that means that our series is going to converge based off of yesterday, okay? But let's use this integral test to confirm for ourselves that it converges. So if I take the integral from 1 to infinity of 1 over x squared dx, okay? Now I would use an integral test for this because this is a pretty straightforward integral. I only need to use the power rule, right? Because this is really like saying x to the negative 2 and taking that integral. And so when we integrate that, we'll get the limit as t approaches infinity of negative 1 over x, and I'm going to plug in t, and I'm going to plug in 1. Okay. So when I plug in those values, I'm going to get negative 1 over infinity minus -1 over 1. -1 over infinity goes to 0. And so we get 0 plus 1, or we get 1. Okay. So the improper integral converges. And what that means is that our infinite series also converge. Okay. Before I show you the rule, which is on the next page, let's kind of look at 4 and 5 again. So with 4, I found my improper integral. I found that it went to infinity, and that diverged. Therefore, I knew that my infinite series also diverged. So whatever the improper integral does, the infinite series also does. And then when we look at example 5, when we took the improper integral, that converged, which matches with what we knew walking into this problem, that infinite series converges.
Is this how you find the sum of what it converges to?
No, none of these tests really give you a sum.
Okay.
Yeah. So here is the integral test, okay? So a few things need to be in place. Our function that we're modeling it after has to be continuous. So we don't want any like holes or asymptotes in the section that we're looking at, okay? So 1 over x is not continuous, but it is from 1 to infinity, so we're okay. All right, so continuous over a given interval. The function also needs to be positive over that given interval, and it needs to be decreasing. So sort of a checklist. Is it continuous? Is it positive? Is it decreasing? If that's the case, then these two statements will be true. If you do your improper integral and you find that it converges, then the infinite series will match that behavior. So if the improper integral converges, so will the infinite series. On the flip side, if you take that improper integral and it diverges, then your infinite series will again match the behavior, and it will also diverge. Okay. So the behaviors match. They kind of go together. If one converges, so does the other. If one diverges, so does the other. Okay. But beyond that, there are some limitations. Okay. So let's just kind of practice this again with 2 more integrals, and then we'll sort of summarize like when might you use this, and then what are some limitations for it. Okay. So example number 6. I've got my infinite series here, okay? And so this is in the section of the integral test. But even in looking at that, I'm like, oh, this is like a U sub situation, straightforward, okay? So I'm going to take my integral from 2 to infinity of 1 over x natural log x. Now, again, I know that this is continuous in this section because I start at 2, and any discontinuities don't happen there because the issues are like 0. What else? What other numbers are an issue to plug in? Negative numbers? Negative numbers, yeah, negative numbers I can't plug in. 1 I can't plug in, right? Because 1 gives me a 0 in the denominator. So that's why this particular infinite series starts at 2, because there's certain limitations. We want to make sure that it's continuous, that it's decreasing, and that it's positive, okay? So let's take our improper integral. We've got the limit as t approaches infinity of from 2 to t of 1 over x natural log x. And this integral, we can use a simple u sub. So u equals natural log x, du equals 1 over x dx. Okay, it's like a very sneaky u sub because everything is in the denominator. So I think sometimes we overthink that, but we can take care of that x in the denominator just by doing u sub. So we'll get the limit as t approaches infinity of 1 over u du. And our integral of 1 over u is nothing more than the natural log. So I have the natural log of, let's put our u back in, the natural log of x. And I'm going to plug in 2, and I'm going to plug in t. Okay. So I know that looks weird because I've got like multiple natural logs, but it's okay. All right, we can still handle that. So we've got natural log of infinity minus natural log of 2. And let's see what happens. Natural log of infinity goes to infinity. So that natural log of infinity, this whole first term, goes to infinity, which means that infinity minus a number is still infinity. And so since this improper integral diverges, we can say that this infinite series diverges as well. Okay, so whatever comes out at the end, that automatically gives you your answer for your infinite series. All right, well, let's try one more example here. We'll talk about the pros and cons, and then we'll take a break. So I look at this one and I'm like, ooh, at first I'm like, maybe I need integration by parts, but I can actually do this just with the u sub, okay? So because I sort of am able to make those decisions, and I think you guys are as well, you did super well in terms of like deciding when to use what rules in chapter 9. This definitely helps with like refreshing a lot of those skills. So since I know I only need u sub, I'm going to try the integral test. Okay. So I have the integral from 0 to infinity of x e to the negative x squared dx. Now, how come I don't have to use integration by parts here?
Because we see part of the derivative, or part of the, yeah, we see part of the derivative in the equation.
Exactly, right? We see this x squared, but we also see the x, and that's actually really good news for us. So let's set up our u sub. I'm going to say, so some people only take like the x squared as the u. I like to just take the whole power, but it doesn't really matter. Like that's kind of up to you, okay? And then du will be negative 2x dx, and negative du over 2 equals x dx. And so now I can say that I have a negative 1/2. The limit as t approaches infinity of from 0 to t of e to the u du. So I get negative 1/2. The integral of e to the u is just e to the u. And that's why I like to just take the whole power. And I don't like to leave the negative sign because I always get nervous I'm going to lose that negative sign somewhere else in my problem. but my e to the u is really e to the negative x squared, and I'm going to plug in infinity, and I'm going to plug in 0, see what happens. So negative 1/2. So I get e to the negative infinity minus e to the 0. Okay. Now I do want your help in seeing what special values come out of this. So e to the 0 gives us what?
1.
Okay, it gives us 1. And I think we all know that. I just think that sometimes we're rushing and we're like, e to the 0 is 0. Okay. What about e to the negative infinity?
0.
It's going to give you 0.
That's going to be 0, right? So like the sign, if you miss the sign here, you're going to end up with like e to the infinity, maybe, possibly. And that would give you a totally different answer, right? So it's not just like a small sign mistake anymore. We have to be really accurate. Otherwise, it gives us something that's totally not true, okay? Now, when we do this, we really have negative 1/2 times negative 1, or we get a value of positive 1/2. Okay.
So will we say convergence?
Okay. Hold on 1 second, folks. There is kind of a large spider running behind my desk right now. I don't know if you guys can see me, but I don't know where it went. I just lost it. Well, now there is a large spider running around behind my desk somewhere. Cool, super cool. Okay, so we get the improper integral converges. So that means that this, our infinite series, also converges. All right. So the behaviors match, right? If with the n we get a convergent value, we're cool. The initial one converges. But if we get a divergent improper integral, then that means that our infinite series also diverges. All right. Okay, so when to use the integral test? The series is eventually decreasing and positive. So you might have a case like, I think we saw this yesterday maybe, where like the function might go up a little bit in the beginning and then ultimately be decreasing. So that is really important here. If it's eventually decreasing and positive and continuous, then you can use the integral test. And the integral test is meant specifically for integrals that are easy to evaluate. So you shouldn't be doing like, you know, multiple different techniques or that kind of stuff. In that case, then it's probably better to choose a different test, okay? So some limitations of the integral test. It only tells you whether a series converges or diverges. It does not give you the value of convergence. So again, that 1/2 is not the value that the series converges to. All that 1/2 tells us is that it does converge. All right. So yesterday we were super lucky in that for telescoping and for geometric, we could find the value, but for most of the series out there, we can't really find the values, and that's okay. All right.
Can I ask one clarifying question?
For sure. What's up?
So on the integral test, we need to make sure that when you look at the function, that it has to be decreasing. Like if you were to take you cannot use the integral test if you, let's say you had you had that same integral that we did above, but it was a positive n squared.
Right, right.
Okay.
If you've got a growth situation, no go.
Okay, sounds good.
Cool. All right, so this seems like a good place to stop and take a break. All right, so we've gone through 2 tests, the divergence test and the integral test. And when we come back from break, we'll take a look at the other 2, which are comparison tests. Okay, so there's a basic comparison test and a limit comparison test. And I'm also hoping to find this little spider. Otherwise, I won't be able to focus for the next hour. But okay, so it is 10:25 right now. Let's meet back here at 10:35 and finish up the lesson today. Okay? questions. Okay, so when you're generalizing the results, make sure to like start with the name of the test, right? Because it's not like anytime you get a number, it means this, and anytime you get 0, it means this. It depends on the specific case that you're using, okay? So I would say when you are using the integral test, if the improper integral goes to a number, then the infinite series converges. If you are using the integral test and your improper integral goes to positive or negative infinity, then your infinite series diverges. Okay, so I would modify that first statement a little bit. And then for the second one, I think that you're talking about the divergence test, right? So when you are using the divergence test and you get, a sub n is a number that's not equal to 0, then it diverges. If it is infinity, that means that sequence just goes up. There's no way that it's going to converge, so that means it's a divergence. Does that make sense, Charmaine?
Can you repeat that last part, Professor? My internet cut out a little
Oh,
bit.
yeah. What was I saying? Okay, so for the divergence test, if the last term is a number, then it diverges. Like a number not equal to 0, it definitely diverges. But if that last number is infinity, your series is also going to diverge, because that means at the end you're adding infinite amounts of something. You're never going to get a converging situation.
Got it.
Okay. Okay. And Carlos, I just saw your question about number 9. We may or may not have time, but let's see, maybe some of the stuff here will help clarify that as well. Okay. All right. So,
Professor, sorry, for the divergence test, so if it's 0, we just try another test, right? Like the integral test.
yeah. Mm-hmm.
Okay.
Yeah. I would think about it less as like an official test and more like you're just ruling out, like it doesn't even converge. So you're not, because some of the other tests are a little bit more work to determine whether it converges or not, or if it diverges or not. So the divergence test is a nice way to say immediately, I know that it diverges. Okay, so to round out today, we are going to take a look at the basic comparison test as well as the limit comparison test. Okay. Now, it's important that when we're looking at these tests, some people like to kind of pick one test and be like, I'm going to use this test for everything, but I would encourage you to really diversify that plan and think about like, when might I use this one? When might I use this one? And if the answer is you could use more than one test, think about like what that's going to look like as you're trying to use the different tests, because they should give you the same answer regardless of what test you use. Okay. So let's take a look at example 8, right? We've got the infinite series of 1 over 3 to the n plus n. And so we've come fresh off of the integral test. And so I can imagine if I wanted to set up an improper integral, it would be the integral from 0 to infinity of 1 over 3 to the x plus x dx. And when I look at that, I'm like, it's not like a quote unquote easy integral. So my decision is no, let's not use the integral test, okay? And it's okay to do that. As long as you feel comfortable with U sub and things like that, the integral test is really good for situations like that. But when we start to get a little bit more complicated, the goal is not to make life as complicated as possible. So there's sort of like this point where we're like, yeah, I don't know that answer, let's move on, okay? So this test, the basic comparison test, does also, like the integral test, want us to have positive terms. So if we look at all of the numbers that could possibly come out of here, could we get a negative number?
No.
No. Good. So positive terms, yep, we're good, okay? Now, let's take a look at a function that might be really similar to this 1 over 3 to the n plus n, okay? Because we're going to compare it to that sequence. So I have 1 over 3 to the n plus n, right? That's my given. Now, I can imagine that as the numbers get really large, right? And that's sort of the key here. As the numbers get really large, like when we go to infinity, that 3 to the infinity, or a large number, is going to get really big really fast. This plus n at the end becomes less important than the 3 to the n. 3 to the n will completely overpower this plus n. And so as such, I can say, well, maybe 1 over 3 to the n plus n is similar to 1 over 3 to the n, okay? See how they're kind of similar? 1 over 3 to the n plus n, 1 over 3 to the n, okay? Now, what happens, like what kind of relationship can we say between our given series and our 1 over 3 to the n? Like, is one bigger than the other all the time? Is one smaller than the other all the time? Does it flip-flop? Like, what's going on?
One will be larger than or one will be smaller than the other.
Yeah, which one is going to be the smaller one?
The one on the left, the one we started with.
Mm-hmm. And why is that going to be smaller?
The denominator will be smaller by n.
The denominator on the left will be larger?
Yeah, the denominator will be larger, making the number closer to 0.
Okay, so the denominator, larger denominator, and that means a smaller fraction, right? So we can say that the one that we came up with that kind of looks similar is actually larger than the one that we started with, okay? Okay, so why is that important? Let's take a look at this 1 over 3n, 3 to the n, a little bit more deeply. So 1 over 3 to the n. If I think about that as an infinite series, I would have something like this. Now this, we could actually also write as this. Does that step make sense to folks?
Yes.
Okay, so I have written it in this other form. The reason why I write it in this other form is because from this form, I can tell that this is specifically a geometric series. And does this geometric series converge or diverge? And how do you know?
It will converge.
So it is going to converge because r equals 1/3, right? R is less than 1, so I know it's going to converge. So if the larger series converges, okay, if the larger series converges, then we know that the smaller series also converges. Okay, so if the larger series converges, so we were able to show that we came up with one that was larger than the one we had. And the one that we came up with, we knew that that converged. That means that our original infinite series also converges. All right, let's try example 9. Okay, let's try example 9. So we have this infinite series. I'm thinking, like I did with the first one, well, what would it look like if I set up an improper integral and I get x over x squared minus cosine squared x dx? I mean, you can integrate it if you want to, but I don't think that it's necessarily one of our quote unquote easy integrals. So I would take a look at that and be like, nope, no thank you. I do not want to integrate that. Let me find a different test, okay? Now, when I'm looking at this, I do want to make sure that I have positive terms, right? So when I look at this, I know my numerator has to be positive. What do I know about my denominator? Anything?
X squared is bigger than negative cosine x.
Okay, but what about the signs? Is it positive? Is it negative?
All positive.
It's all positive, yeah, because I have a positive number squared, and then what's the biggest that cosine can be?
1.
Yeah, it could be 1, and that can't be any bigger than that. So 1, the smallest that it can be is that it's going to be 0, but every other term is going to be positive, all right? So we're good with the positive term. So let's take this original series. I've got n over n squared minus cosine squared n. Okay. And let's think about what it could be similar to, okay? Now, this is the tough thing, I think, about the basic comparison test. you have to really know your different series and what it could look like and what that series does, okay? So when I look at this, here's my process. I'm like, all right, cosine squared is really just saying like I'm subtracting 1 at the worst, right? Like I'm not really changing the denominator that much because it's only subtracting anywhere between -1 and +1, and it's squared, so only 0 to 1. So then I'm like, well, if I sort of ignore that cosine squared, I end up with n over n squared, right? And then I'm like, well, n over n squared is really, n over n squared is really just 1 over n when I sort of distribute, or not distribute, when I ignore and cancel some of the terms there, right? N on the top, n on the bottom, those reduce to 1, and I get 1 over n. So let's compare 1 over n with n over n squared minus cosine squared n. Which one is going to be bigger or smaller, and why?
The 1 over n will be bigger according to the cos, or the other one has the cosine squared n.
I think the cosine's gonna be greater.
Okay, well, let's think about this. I have cosine squared. The maximum value of that is 1. So really, the worst case is it looks like n over n squared minus 1 compared to, let's try this one, n over n squared. Which one of those is bigger and why?
She's right.
Yeah, that left one is bigger because this has a smaller denominator, not by much, but enough to know that it's a smaller denominator, which means that our original one is actually larger than the one we came up with, 1 over n. Okay. So now let's unpack what we know about 1 over n. So if I have the infinite series of 1 over n, I know that that is, now we can say it's a harmonic series, right? Harmonic series, or special case P series. Harmonic, it diverges, and it's smaller than the one that we're comparing it to. So we can sort of flip-flop this statement we wrote earlier for a situation where it's converging to say something like this. If the smaller series diverges, then we know that the smaller, the larger series also diverges. Okay. So if the smaller series diverges, then we know that the larger series also diverges.
So the behaviors match on both cases?
Yes, as long as like the larger one converging means the smaller one converges. But if you saw a smaller one that converges, it does not tell you that the larger one converges. That makes sense? Okay.
Yeah.
Yeah, so it has to be the larger series converges, then the smaller one will also converge, okay? And then if the smaller series diverges, then the larger series also diverges. I was kind of thinking about, like, you know, let's say you're running a race or something. If I'm ahead, like let's say that I was running a race and I was running with someone that was slower than me, right? And let's say that nobody knows what their times are, but I cross the finish line and then this slower person crosses the finish line. If they ran the race in 20 minutes, it means I ran the race faster than 20 minutes because I finished ahead of them. So that's kind of like this smaller one diverges and the larger one does too. And then the other one, if the larger one converges, we know that the smaller one converges. You can think about that like, oh gosh, what's a good example? I can't think of one right now, but it does matter like which one is bigger and which one is smaller. And that in fact is one of the limitations of the comparison test, okay? So let's actually take a look at the official comparison test in like math language and then think about the pros and cons for this. So the comparison test says this. Suppose we have two series, a sub n and b sub n. Okay, so a sub n is like your original one, b sub n is like the one you make up. So original, created one. All right. And you know that they're positive for all the values. And you know that there is some sort of comparison between them, okay? If the one that you're comparing it to is larger, if the larger one converges, so does the smaller one. If the smaller one converges, then so does the larger one, okay? But let's take this idea, let's practice one more time with like coming up with the b sub n, because I think that is an important skill that will carry over into our limit comparison test, okay? And some people find the limit comparison test to be a little bit more straightforward, but it doesn't matter. Most of the time you can use one or the other, but only if that bigger, smaller piece is there, okay? So let's take a look at this example here. So I've got my infinite series. I look at it and I'm like, I don't want to integrate that. So we'll take that off the table. And then I'm going to write down the series that we have, my a sub n, my a sub n. And then I'm going to compare it to another series. So what might be a good series to use here?
1 over n squared.
Yeah, backtrack that for me a little bit. How did you get 1 over n squared?
N squared over n to the fourth.
Good. Okay, so for those of you who maybe aren't sure where she got that from, she just kind of looked at the bigger power here and the bigger power here, right? Because at the end, when we're adding 2 and 5 to infinitely large values, it doesn't really impact it that much. So these two should have very similar end behaviors, okay? So now, let's see which one we think might be bigger or smaller. What do we think? A lot.
N squared over n for the plus and one pluses is going to be smaller than the other.
Why do you say that?
Because the denominator gets bigger and you're dividing, it's approaching a smaller number.
It is, but so is the numerator. The numerator is also getting bigger because I have a +2 up there. Right, so this one's a little tricky. It's a little tricky because we can't say like we did earlier where there was only a number in the denominator changing that value. We now have to consider not just the 5, but also the 2, okay? So here's what we're gonna do. We're actually gonna take a little bit of an intermediate step, okay? And we are going to see what happens if we just kind of ignore the 5 for a moment, okay? So if I ignore the 5, I'm gonna get n squared plus 2 over n to the 4, right? So I've just kind of dropped the 5 here. Now, what that allows me to do is split this into n squared over n to the 4th plus 2 over n to the 4th, right? So basic fraction rules, I can split something with 2 numerators into 2 different fractions. So in this case, if I have n squared over 4, or over n to the 4th, plus 2 over n to the 4th. Now let's think, how does that compare to our original one? N squared plus 2 over n to the 4th plus 5. Okay. So if we put them back together, maybe that makes it easier to see. Which one of these is bigger and why?
The left,
The left is bigger because
right, is always gonna be 5 bigger on the denominator, which makes it smaller since it's on the denominator.
Yeah. So this one that we created is larger than the one that we're comparing it to. Now, n squared plus 2 over n to the 4th is maybe not the best form to determine what's happening in terms of convergence, which is why we can sort of break it down into 2 parts and see what happens to each part. So if we break this down, we really have 1 over n squared plus 2 over n to the 4th. 1 over n squared, does that converge or diverge?
Convert.
Yeah, this one converges. And so does this one, because they're both p-series where the p-value is larger than 1. So let's go back to that statement that we said earlier. If the larger series converges, so does the smaller one. So right here, we can say if the larger series converges, that's the one we made up, so does the smaller series. Okay, so if the larger series converges, so does the smaller series. So when we look at this, it's really, I think this is sort of the part of the basic comparison test that's maybe not so basic, that it's a little bit complicated because we're used to, you know, maybe some of the other ones were a little bit more straightforward, but in this case, we only dropped the 5. We didn't drop the 2, right? So that's sort of Abby's question right here. How would you decide what you need to ignore a number? And I think the best answer to that is a terrible answer as someone who's learning this, which is you just kind of got to try and see what happens. Can you draw a definitive relationship between the one you created and the one that you're given? And when I stripped away the 2 and the 5, I couldn't say for sure what that relationship was because the 2 and the 5 are both contributing factors. So then at that point, it's kind of a good strategy to take a step back and say, instead of getting rid of everything, what if I kept the same idea from before, which is if one of the denominators is bigger, then I know that fraction is smaller. And so that's why I chose to keep the 5, but get rid of the 2. Get rid of the 5, but keep the 2. Does that make sense?
Yes.
Yeah. It's a lot. It's definitely a lot. And that I would say is perhaps the biggest drawback to the basic comparison test, okay? Is that you at times have to be creative about what you're comparing it to. You cannot just assume that something is always bigger if you're not sure. You really have to be able to mathematically show it is in fact larger, okay? So when to use the basic comparison test? If you have a series that is positive, great time to use the basic comparison test. Also, if it compares to a nice series, specifically if it looks like a p-series or it could be a geometric series. Those are sort of our go-to, okay? If you have a rational expression, meaning something over something else, that's probably a good time to use the basic comparison test, all right? Some limitations. It only tells you whether it converges or diverges. It doesn't give you the value of convergence, but maybe we should add one that says can be challenging to find B sub n. All right. So it can be challenging to find a B sub n. So sometimes we have to be a little bit careful, like in example number 10. All right. So we've got one last test to take a look at, which is the limit comparison test. And I tend to find that folks like this one a little bit better than the basic comparison, because it feels more like the integral test in the sense that the answers kind of match, and I think that's kind of nice. All right. So here's the limit comparison test. You have your given series, a sub n, and you have one that you create that you compare it to, the b sub n. So those are the same as before. Okay, so a sub n is your given, b sub n is your created one that you're going to compare it to. Now, if you take the limit as n approaches infinity of their ratios, a sub n over b sub n, and you get a number. Okay. Go through all that work. If C is positive and finite, so positive infinity doesn't count. 1,000 counts. 1/2 would count for C. But if the C is positive and finite, then both series converge or both of them diverge. So that's the part that feels kind of like the integral test to me, where you get a number and then at the end they both do the same thing. You don't have to know which one's bigger than the other. You just know that they do the same thing. Okay. And I think that's why some people prefer the limit comparison test to maybe like the basic comparison test. All right, so let's take a look at this example. Okay, so we have this infinite series, 1 over 3 to the n minus n. So it's kind of similar to what we had when we were looking at the basic comparison test, all right? But what we're gonna do now is we're gonna say, like, what could we compare it to? And how do we set up this limit comparison test? So what would be a good, what would be a good b sub n to compare this series to?
1 over 3 to the n power.
1 over 3 to the n. Yeah, because when we go to infinity, that minus whatever number is going to matter less, but that 3 to the n is going to be so much more powerful. Okay. Now, let's set up our limit comparison series, limit comparison test. So I'm going to take the limit as n approaches infinity of, now here's the deal. I could write it like a sub n, that's my a sub n, right? Now, divided by b sub n really means times the reciprocal of b sub n. So sometimes instead of writing it the way that this formula does, I write it like this: the limit as n approaches a sub n times 1 over b sub n. Okay. And actually, it doesn't matter whether we do a sub n over b sub n or the other way around. Okay. So this could be also the limit as n approaches infinity of b sub n times 1 over a sub n. So in that sense, you can flip whichever one you want to flip. Okay. Now, for this problem, this is just like one way I could set it up. And that would give me the limit as n approaches infinity of 3 to the n over 3 to the n minus n. Okay. Now, it doesn't really matter here. I did this problem the other way. So I had the b sub n on the top and the a sub n on the bottom. But I'll show you why I chose to do that. But ultimately, your answers will be the same. So I had 1 over, I have my 1 over 3 to the n, that's my b sub n, times 1 over a sub n, so 3 to the n minus n over 1. And the reason why I chose to do it this way, though again, it doesn't matter, is because when I combine my fractions, I get to a situation where I can actually split it, so I get 1 minus n over 3 to the n. So it just allowed me to do a little bit more algebraic simplification before I took the limit, but it does not matter. Okay, it doesn't matter which setup you use. If we sort of continue with this particular setup, just for this example, I know that when I plug in infinity, I'm going to get 1 minus infinity over infinity, which means that I have to use L'Hopital, okay, for that second part, that n over 3 to the n. So I'm going to get 1 minus the limit as n approaches infinity of the derivative of n is just 1. The derivative of 3 to the n, we don't see this often, but it's 3 to the n times the natural log of the base, which in this case is 3. And now when we plug in infinity, we get 1 minus 1 over infinity, or 1 minus 0, or we get 1. Okay. So we get 1. Let's go back and see what that means. That means C is 1. That means C is positive and it's greater than 0 and it's finite. Okay? So let's go back to our comparing series, this one right here. Does that converge or diverge?
We don't know.
We do know.
Convert.
It does converge, yeah, because remember, this is our geometric series. The one that we chose one that we should know what happens to it. Geometric series, r equals 1/3, so this one converges. And since this one converges, it means this one converges. Because their behaviors have to match if I get a positive finite number at the end. All right. So before we go over the last example, just pause here for a moment. Does anybody have any questions right now?
I just have a question on the test that we just did. So the test, this comparison test,
The limit
I understand
comparison test or the basic comparison test?
I'm sorry, the limit comparison test. So with the limit comparison test, your B of n, we chose one that we know what the end behavior is. But the limit comparison test is just stating that either both will converge or both will diverge. And so we choose a similar graph that is easy to determine whether it converges or diverges that way. Once we sit there and say, okay, they both behave the same way, then we can say that they both converge or they both diverge.
Right.
Okay.
So it's very similar to the basic comparison test. Like your B sub n is the same, right? You pick one that you know what's going to happen with it. But I think sometimes like you don't have to determine which one is bigger or smaller for the limit comparison test. Whereas for the basic comparison test, you do need to know which one is bigger or which one is smaller.
Okay. With the basic comparison test, we just know that the behavior of the larger graph is going to match the behavior of the smaller graph. If we, right?
It depends if you're looking at convergence or divergence. Like if the larger one converges, then the smaller one does also. However, if the smaller one diverges, like if you're looking at a divergence case, like the behaviors match, but you have to know that the smaller one diverges.
Oh, okay.
Okay.
So only on convergence, the larger one will match the smaller one, and only on divergence, the smaller one will match the larger one. It doesn't go the other way.
Correct.
Okay.
Yeah.
Now that that's cleared up, got it.
Okay. All right. So we've got one last example, and then we'll talk about some pros and cons. All right. So we've got this infinite series. We have 4n squared plus n over the cube root of n to the 7th plus n to the 3rd. Now, immediately, I hope that nobody's trying to integrate this, okay? That is like a bad call. It just like, it's not gonna go very well for you, all right? But with the radicals here, all right? So radicals, I think, are actually a good time to think about our exponent properties, and that can really help us determine that b sub n, okay? So when we're determining the b sub n, what I like to do is find sort of like the dominating power on the top and the dominating power on the bottom, because if they're all variables like we have here, then it will be like the one with the highest power will have the most impact on the end behavior. So if I look at the top, I know that I have like an n squared situation, right? The highest power on the top is n squared. So I'm going to say that my numerator for my comparison series is going to be n squared. Now, in the denominator, though, the highest power is not 7. What is the highest power?
7 times 1/3.
Yes, 7 times 1/3. Okay. Can you explain to us where you got that from?
Because the cube root would be to the 1/3.
Good. So to find that highest power, if we're looking at a radical, you have to incorporate that radical. That means the power on the bottom is going to be n to the 7/3, like the dominating power. Now let's go ahead and simplify this a little bit because I know that I'm going to have to multiply some things, okay? So when I simplify this, I get 1 over n to the 1/3. Now 1 over n to the 1/3 is a series that we know some stuff about, right? So this is a p-series. Does this p-series converge or diverge?
Converge.
How
Not
do you,
yet,
Diverge.
how do you know that?
because
It's less than 1.
p is
Yeah,
less than 1.
p is 1/3. That's less than 1. That means that it diverges. Okay. So again, it's really important. Like the stuff we learned yesterday is so fundamental because if we're going to compare things, we need to know that, or we need to make sure we know what's going to happen with it, right? Because one misstep here means that at the end, we're interpreting our results in a way that's not necessarily making sense, okay? So we've got our b sub n. We already know what happens to it. We know that it's going to diverge. So if we get a number at the end of our limit comparison test that is positive, that is finite, then we know that this messy looking sequence that we have here, or this messy looking series, will also diverge. So let's set up our limit comparison test. This time I'm going to keep my a sub n the way it is. And I'm going to multiply by 1 over b sub n, which is going to be n to the 1/3 over 1. Okay. Again, you could flip whichever one you feel more comfortable with. It doesn't matter, but don't flip them both. You only flip one of them. Okay. All right. So let's do a little combining. We're going to get 4n to the 7/3 plus n to the 4/3 on the top. And we have our cube root of n to the 7th plus n to the 3rd on the bottom. Okay. So all I did was distribute that n to the 1/3. Now I'm going to keep the denominator, or keep the numerator the way it is. And what I'm going to do to the denominator is in here, I'm going to factor out an n to the 7th. Now that's going to leave me with 1 plus, how do I get to n to the 3rd?
It's 1.
n to power minus 4.
Yeah, 1 over n to the 4th. If I distribute that back in, it will give me n to the 3rd. Okay. Now, you might be like, well, why would you choose to do that? And how do I know to do that? And that's because I see a fraction here. So I'm thinking about the shortcut that we started today's lesson with. If I can get a same power on the bottom as I can on the top, then I can, instead of having to use L'Hopital, I can just say, hey, I know what that n behavior is going to be. So look at what we did. Whoa. I have created this n to the 7/3 that I can pull out of the radical. And what's left is that inside. Now, if I plugged in infinity over infinity, or infinity here, I would get infinity over infinity. I would have to use L'Hopital. But that means taking a derivative of some things I really don't want to take the derivative of. So let's use our shortcut, which is when the power on the top is the same as the power on the bottom, I can just take the ratio of the coefficients to get my end behavior. That means the limit comparison test gave us the number 4. 4 is positive, 4 is finite, so it will follow the behavior of my b sub n. So this will also diverge. All right. So folks, that is it for today. I know that's a very full day and perhaps ramped up significantly from yesterday, but yesterday's stuff is still important, right? Because it helps us figure out whether we are comparing things to things that we know what's happening, like this p-series, or maybe it's a geometric series, but it all goes back to how can we get as close to something we know as possible, and then how do we interpret our results, okay? Are there any questions on today's lesson before I stop sharing the screen? All right.